Hello and welcome to this video. And in this video we're going to talk about rational functions, and we're going to add in this idea of slant asymptotes. And we've briefly talked about slant asymptotes in a previous video, but we're going to expand on that a little bit now. So if you look at f of x here, on the top you have a degree of 2. Okay, so I'll say the numerator has a degree of 2. The denominator has a degree of 1, and when the degree of the numerator is greater than the degree of the denominator, so let's say degree of numerator is greater than the degree of the denominator, we already know that you do not have a horizontal asymptote. Okay, the horizontal asymptote only happens when you have a degree on the top and the bottom that are the same, or maybe when the degree of the bottom is higher than the top. Okay, so in this case we already know we do not have a horizontal asymptote. And so what happens here, if you look at the degree of the numerator here is 2 and the degree of the denominator is 1, we will have this slant asymptote. Now the difference here between 2 and 1 is 1. Okay, so if you do take the difference of the 2 degrees and you get a difference of 1, that's when you specifically have this what we call slant asymptote. Okay, now if you have a function where the degree of the numerator is greater than the degree of the denominator, so let me just actually make one up here real quick to show you. So let's say g of x is like 4x cubed plus 2x plus 6. And I'm literally just making something up here. And then the bottom is say x minus 4. Okay, so the degree of the numerator, right, the degree of the numerator is 3 and the degree of the denominator is 1. Well, this is also not going to have the horizontal asymptote, but the difference is 2, right? So when you take 3 minus 1, you get a 2, and this is what we call an oblique asymptote. Okay, so it's a little bit different than a slant. A slant asymptote is always linear. Okay, it's just going to be a line. An oblique asymptote can have a lot of different looks to it. It can have a quadratic look or cubic look and that kind of thing. And that's something that you will do more with later down the road. We just like for you to know that that does exist. And for this class, we like to focus on the slant asymptotes. So if you look at back to f of x, and we know it has the slant asymptote, the way you find your slant asymptote is using long division, okay? And so you can also use synthetic when that's applicable. So if I take the x minus 1 and I put it outside of the function, I can do my long division and see what I get there. Or in this case, since synthetic is applicable, you may want to use that. Okay, and so let's see here what we'll get. Okay, so in this last spot we'll get a 2, which is the remainder. And here we have y equals 3x plus 1, okay, which is obviously that slant asymptote that was given. So that polynomial long division or synthetic, you want to ignore that remainder, okay, that absolutely plays no part in the result of that slant, and you use the other parts of the division to figure out the equation. So similarly, if you would have done your long division, you would have gotten your 3x plus 1 up here, and you would have had some stuff. Okay, but either way, you're going to get that 3x plus 1. Okay, now when you graph a slant asymptote, you just graph it just like following your y equals mx plus b format, where m is the slope and b is the y-intercept. So in this case you have a y-intercept of 1, okay, and then you have a slope of 3. So they're going up 3 over 1, up 3 over 1, okay, and they're generating that line. And then you would also find all of the other things that we already know how to find. You'd want to find your vertical asymptote, you'd want to find your x-intercepts, y-intercepts, okay? And then you want to think about your domain. And then also remember that sometimes you still need to find some more points, and you would do a table of values, pick some x values that you are interested in, calculate those y values, and plot those points. Okay, so that's a quick little introduction there to what we're doing with slant asymptotes. Let's go down to this example here and work through it. So we know we're going to have a slant asymptote, okay, and we can go ahead and find the equation of that by doing our synthetic division. Remember to put in placeholders when it's applicable. All right, and we're going to get y equals x plus 1 as our equation for that slant asymptote. Okay, and remember you can just completely ignore this remainder right here. Okay, so we also know that we're going to have a vertical asymptote at x equals 1, okay, using the denominator here. We can also think about like a y-intercept, right? You can plug in, evaluate your function for 0, and do some quick calculations there, and you're going to get -1. So we know we're going to have a y-intercept of -1. And actually, let's go ahead and start sketching some things here. So vertical asymptote at x equals 1. We have a y-intercept at -1. We can go ahead and graph our slant asymptote. It has a y-intercept of 1 and a slope of 1. So we're going up 1 over 1, up 1 over 1. Okay, and that would look something like this. Okay, think of those lines going forever there. Okay, and remember we typically make our asymptotes dotted. And then you could find your x-intercepts. So you want to think of setting the top equal to 0. And x squared plus 1 does not factor. So we'll just rely on our algebra here. Well, what happens is you end up having to take the positive and negative square root of -1. And as we know, that gets us into the imaginary number system there. So that means we actually do not have any x-intercepts, okay? So we're using all of this information to figure out what's going on with the graph. Now, if you think about the domain of the function, okay, the only thing I have going on with my domain is that x can't equal 1. So I have -infinity to 1 union 1 to infinity. So I know that there is 2 sections to this graph, right? I need to think about 2 sections of this domain. And it's kind of easy to figure out what's going on in this bottom section because we have a y-intercept, and so we know it's going to go down there. And then we know it's going to kind of go maybe that way-ish because of that slant asymptote. Remember, those asymptotes are going to steer the graph in the direction that you want it to go. So we've actually taken care of this section of the domain here because the graph that we just figured out, but we still need to figure out what's going on in this section of the domain, and here's where you're going to need to do a table of values and find a few points. Okay, and so just pick some x values in that section, so maybe like 2 and 3, and you're going to plug those in and calculate what you're getting. So I quickly calculated those, and you actually, when I use 2, I get a 5. When I use 3, I get a 5. And so if we go back to our graph here, if you want to think about going over to an x value of 2, you would need to go up to 5. So let's say it's up there somewhere. Then an x value of 3 would be 5, something like that. And then you just want to follow those asymptotes, okay? So we know it's going to kind of come down, kind of curve, and then it's going to go that way because of the asymptote. And then we know it's going to go up because of the vertical asymptote. And something like this is plenty good for your sketch, okay? So at this point, like I said, you're just focusing on finding this asymptote, okay, and then putting that together with the information you already know about rational functions, and then getting some sketch. And like I said, it doesn't have to be super accurate, it just needs to generally represent the main parts of the function. All right, and ask questions when you have them. I'll see you in the next video.